Interaction with non-rigid objects such as garments, bedding, or various food items is required in many of our daily activities. And while tasks like changing the sheets on the bed, folding clothes, or kneading pizza dough come almost natural to humans, they still pose a tremendous challenge to robots. This is mainly due to the complex dynamics and high-dimensional configuration spaces that these deformable objects exhibit. We envision a future where robots are not only useful in the industrial production halls, but can assist us in our daily lives at work and at home. To do so, we believe that it is crucial that robots gain the capabilities to manipulate not only rigid, but also soft objects. And since we want them to be skilled and effective associates, they need to be able to do it in a dynamic and efficient manner. To this end, we investigate how to leverage model-based trajectory optimization techniques for dynamic manipulation of deformable objects. In this work, we make use of a dual-armed Yumi robot and different types of elastic objects made out of foam. Our computational framework generates optimal nominal control trajectories in the robot's configuration space that can then be passed onto the physical platform. We test and analyze our implementation by experimenting with several tasks for the Yumi to carry out. For example, the goal here is to knock the wooden target off the table with one single swipe of the soft rod. We formulate this problem by modeling the elastic objects using the finite element method. In brief, FEM considers a discretization of the manipulated object into a volumetric tetrahedral mesh. The positions of all mesh nodes are assembled into a vector xi, which constitutes the state of the object at the specific trajectory step I. For more information about FEM, we would like to refer you to the paper. The robot is modeled using its kinematic chain and its joint angles. All angles are stacked into the vector ui, which describes the controls applied to the system at step I. The individual targets of all conducted experiments can be incorporated by including objectives into the overall optimization problem in form of quadratic penalties. These penalties match a specific mesh node to a target in world coordinates at the given trajectory step. Trajectory optimization problems typically appear in this form, where L and LF are running and final costs, and F denotes an explicit transition function incorporating the system's dynamics. While this problem can be solved directly using a constrained optimization method, the drawback of this approach is that the candidate solution can only be considered physically correct once the constraints are satisfied. This is why we center our attention rather on single-shooting methods that leverage forward simulation. They bring the advantage of generating physically plausible solutions at each iteration. Specifically, we investigate and compare the performance of two different optimization strategies: Newton's method and differential dynamic programming. Briefly, Newton's method is a batch approach that optimizes the entire trajectory simultaneously and therefore often treats it as a general optimization problem. In contrast, DDP is a stage-wise method that processes the control sequence recursively, starting from the end of the trajectory. In this talk, we are going to focus more on the application rather than the comparison of these two methods. More details about how they differ in their formulation and performance are presented in the paper. The main challenge when we want to simulate deformable objects for dynamic manipulation is that they suffer from numerical stiffness issues. As a consequence, when applying explicit integration to these types of systems, the simulation tends to be unstable and blow up quickly. This has been verified by several independent works over the last few years and has been confirmed by our own experiments as well. These issues make explicit integration unviable for simulation and control of soft objects, as they fail to reliably predict motions. Therefore, in our experience, these systems can only be stably handled by applying implicit integration schemes. For this reason, we convert the explicit state function f into an implicit function g. Consequently, g is not only a function of the state at step i+1, but also of the acceleration. Since we formulate our problem in a discrete manner, we approximate this acceleration with a backward differentiation formula, where h denotes the time between two consecutive trajectory steps. We stack all past trajectory steps together and denote them with capital Xi. We note that we can use higher order approximations of the acceleration by simply including more past trajectory steps into this variable. We can then adapt our optimization problem to look like this. We can see now that g not only depends on the current state to be computed, but also on past trajectory steps. Similarly, we consider cost functions that depend on previous states and controls as well, since this allows us to put objectives on velocities and accelerations of both control and state variables. By doing so, we end up with a very similar formulation as the standard one from before, which allows us to solve this problem in the same manner. The main difference to before is the implicit transition function g. To apply trajectory optimization techniques, it is crucial that we are able to take derivatives of this implicit relation between x and u. Specifically, we need to know how xi+1 changes with respect to its past time steps, as well as the control input that is currently applied. Fortunately, these derivatives are available by using the implicit function theorem, and therefore we end up with explicit expression for these terms. Using this derivation, we can now have a numerically stable forward simulation and its derivatives, which can be used to find optimal control inputs for the robot via trajectory optimization. As mentioned before, we test this formulation on different examples in the context of dynamic soft body manipulation. The robot's goal here is to lay a sheet onto the table, once using a single and once using both arms. We also conducted several experiments to investigate the extent to which these simulated results carry over to the real world. To this end, we sent the in simulation computed control commands to the physical robot in an open loop manner. These two examples here show similar strategies as seen in the simulation results before. We note that since we are using a model-based approach, our framework relies on a simulation model that accurately captures the behavior of the physical objects being manipulated. Using different model parameters that, for example, lead to softer or stiffer meshes, not only influence the simulation, but naturally also result in different control strategies for the same overall goal. Therefore, the success of sim-to-real transfer hinges on accurate model parameter estimation. For our experiment, we calibrated the model parameters to roughly fit the physical counterpart in the quasi-static case. While this simple approach usually puts the parameters in the correct ballpark, mismatches typically still occur for more dynamic motions due to model approximations. An example of such mismatches can be seen in this side-by-side comparison. Although the robot generally succeeds with its task, it can be seen that the simulation model predicts that the lower end of the soft sheet will lift up higher than it does in reality. Recently, methods have been presented which track and analyze the motion of physical prototypes in order to accurately reconstruct their material parameters. How to include these techniques into our framework to further reduce the reality gap will be part of future investigations. Another interesting future avenue to cope with these problems is to include feedback control into the current feed-forward process. How this can be done best is a research question that deserves its own investigation. To summarize, in this work, we develop, validate, and analyze model-based optimal control techniques for dynamic manipulation of deformable objects. We do so by extending the common trajectory optimization formulation by the use of an implicit integration scheme. We study both the batch-Newton method and the stage-wise DDP approach and compare their performance in the context of our problem setup. Detailed information about this comparison can be found in the paper. Finally, we conduct a variety of simulation and real-world experiments. Closing the reality gap with approaches like improved parameter estimation or feedback control will be part of future investigations. We conclude that even with only approximate soft body models, the robot can already successfully execute tasks in a dynamic fashion. Thank you very much for your attention.